Okay, thank you very much. I'd like to thank the organizers for giving me the opportunity to speak. Thank you all for sticking it out to the end of the day. And I should apologize because I'm going to try and cover too much material, but hopefully we'll all survive. This is work that I've done with a number of different people. One of them, Luis, is sitting here. We heard from him earlier in the day. There's also Alex Bushel, two students, Anton and Damien, back at Perimeter, and Sumit Das in Kentucky. So my title, Quantum Quenches and Holography. Most of us here are holographers, and so I should say a little bit about the first half of that title, Quantum Quenches. What is a quantum quench? Basically, we take our favorite quantum system and we kick it. So in the language of Physics 101, what that means is we've got some Hamiltonian that governs the evolution of that system, and then we're going to change it by adding a new operator through some coupling. And what we want to do is the coupling originally is off, but then we'll rapidly turn it on. And we're going to prepare the system in some eigenstate of original Hamiltonian, but we want to watch how it evolves then under the evolution of our new Hamiltonian. And we might ask, how do expectation values change? How do correlation functions change when we give it this kick? Of course, the answer is that typically what happens is a big mess, because much of the evolution is not controlled by that Hamiltonian, but how our system is actually coupled to other sources or other systems in the lab. And so most of that physics is governed by things like dissipation and decoherence. However, recently the experimentalists have been very clever, worked hard, and established systems where in fact we can avoid, to a large extent, this coupling to the external world, and so we can really watch the system evolve according to the Hamiltonian of interest. And so, for example, they deal with cold atoms in an optical lattice. And so as a theorist, or as theorists, we might ask, is there some kind of universal behavior? Sorry. Okay, thank you. Kind of universal behavior that we can see evolution, or what are the organizing principles of systems out of equilibrium? Now, as I said, the experimentalists have made progress, but that's attracted a great deal of attention from theorists, and they've worked on a variety of different systems. But in particular, very special systems, so two-dimensional conformal field theory. Really? I don't believe you. Free fields or special integrable models. And it's not fair to say that there hasn't been much progress, but it's fair to say that one is still looking for broadly applicable or efficient techniques to describe this out of equilibrium physics. Now, this certainly looks like an interesting nail to hit with our holographic hammer. ADS-CFT certainly has a number of characteristics that lend it very nicely to this kind of system or this kind of physics. We would be studying strongly coupled field theories. Real-time analysis is available. We can introduce a finite temperature if we like, and I'm also going to show my pedigree as a string theorist by saying, and the space-time dimension is another parameter that we get to dial in the problem. But more generally, just ADS-CFT is going to force us to reorganize the problem, reorganize the way we look at it, and so that by itself may lead to new insights. Of course, I and my collaborators were not the first people to start studying this. There's been a lot of activity in recent years studying these kinds of this kind of physical evolution in ADS-CFT. However, most of the people, or at least
over half of the people here wouldn't know that they were studying quantum quenches. Instead, their work was aimed at the problem of thermalization, or now perhaps hydroization. It's also true that, well, I would have characterized much of the analysis as studying exotic systems, in that one could make nice analytic progress by using things like the Vajra, but perhaps one might think that that's not the most realistic setting in which, or the best we can do. These two gentlemen, Chesler and Yaffe, head up the list because they really decided that there are interesting dynamical problems in ADS-CFT, and we should just bite the bullet, work hard, and solve. And so they really paved the way for applying numerical techniques to studying these kinds of problems in the ADS-CFT. And we're really just following in their footsteps. And before I go much farther, though, I wanted to put one review slide in there for the 2 or 3 non-holographers in the audience who might still have stuck it out. And so I wanted to tell you, where do we get the levers and knobs with which we're going to do our quantum quench. So we wanted, and that's just basic ADS-CFT dictionary. We want to introduce new operators in our boundary theory, but those operators are going to be dual to some fields in the gravitational or in the bulk. And so, for example, if I have a scalar, it's going to satisfy some second-order equation. There are going to be 2 independent solutions, and if I look asymptotically at large r or near the boundary of ADS, the 2 independent solutions can be characterized by their fall-off, and these coefficients, these integration constants, then are associated with the coupling and the expectation value of our new operator. And of course, these exponents, well, I've written them in terms of the dimension of my operator, but they're related, of course, to the mass of the scalar and the radius of the ADS, and also the dimension of our boundary spacetime. So what does a holographic quantum quench look like then? Well, here we have, in cartoon, just empty ADS. And what I'm going to do then is I'm going to choose an interesting profile for my coupling. So it's going to start here at 0, and over some fairly short amount of time, I'm going to turn it on. And so as Franz was emphasizing, this is the part of the solution that I get to choose. So this defines my protocol, or my how I'm kicking the system. On the gravitational side, what does that kick do? Well, I'm really pulling the end, or tickling the scalar field, and so I'm launching a bunch of waves, scalar field waves, into the ADS space. And if we look carefully at the solution, if we look at the tails at the boundary, then what we're going to do is we're going to pick out that other constant, or the other solution, and that's going to be telling us then about the response of the system, or the expectation value of that operator. Of course, on the gravitational side, what does that look like? Well, that looks like a gravitational collapse problem. And in the kinds of kicks that I'm going to be giving it today, there's no bouncing around. It just collapses and forms a black hole. And so, of course, on the dual side, what that means is the system settles down into a thermal state. In fact, I'm going to do something a little bit different. Rather than starting with empty ADS down here, I'm going to start with a black hole, at least in the first part of my talk. And so I'm doing then what we called a thermal quench, or a quantum quench at finite temperature. Rather than starting with the ground state, I'm starting with a thermal ensemble. I'm kicking it here, and so the black hole grows and it settles into a new thermal state eventually. But there's still this interesting evolution that we can follow. Now, in fact, what did we do then? Well, as I said, we had to choose a bunch of things, and so in this work with Luis, Anton, and Alex, the first thing we did is, well, we basically settled on d equals 4. We looked at relevant operators, or in fact, we also included the marginal case. So the scaling dimension ranges from 4 down to 2. That means that my bulk field ranges from being a massless field down to the BF bound. And we chose some simple profile that looked like this. Here's the amplitude, delta lambda, and then there's this tangent that takes it from 0. Well, if I add the 1, it goes from 0 up to delta lambda in a narrow window around t equals 0, and the size of that window is characterized by this scale delta t. Now, we've heard a lot about impressive numerical simulations today, and we'll hear more later this week. What did we do? Well, we were just getting our feet wet, and so all we really solved for was the linearized scalar field equation in the fixed background of the ADS black hole. What you can think that we're doing is a perturbative expansion. This black hole gives me an initial temperature, that gives me a scale. This delta lambda also gives me a scale, and so I'm working perturbatively in the ratio of those scales. The delta lambda scale over t is much, much less than 1. And within that perturbation expansion, then, we can find, as I described, just by solving the linearized equation, the leading order response to this kick. Now, that was a pretty wimpy start, and you may think that I'm going to work hard now and do a difficult back reaction problem and work to higher orders and find how the mass of the black hole changes throughout my kick or my quantum quench. But in fact, I'm going to disappoint you because I'm not going to do that. I am going to solve for the mass or the energy density, but I'm just going to use what on the CFT side we can call a diffeomorphism word identity, or on the Einstein side, this is just a constraint in the Einstein's equations, which amounts to the same thing as this word identity when I push it back to the boundary at r equals infinity. But essentially what this constraint is saying, it's talking about energy conservation. Here's the divergence of the stress tensor. Ordinarily, we're used to seeing a 0 on this side of the equation. But in doing the quantum quench, we're working on the system. And so there's a source term on this side. In particular, where the situation here where we have a uniform quench or a uniform coupling that only evolves in time, the interesting equation is the time derivative of the energy density being related to the expectation value times the time derivative of our coupling. And so I know the energy density that I started with. I just integrate this up, and I can find the energy density that I end up with, or in fact at any time along here. So given that, 138 pages later, what have we learned? Well, we've learned quite a few things, but I'm only going to ask you to remember 2 of them. So the first one is that the renormalization of the quantum field theory, the Bounham quantum field theory, works in a straightforward way, even when we're working with time-dependent couplings. And this is a lesson learned that was in our paper. I didn't really appreciate it until more recently when I've been doing non-holographic things, but it's really an important lesson. Here we have some complicated, strongly coupled quantum field theory, but holography gives us a well-defined approach by which we're going to renormalize it in the presence of time-dependent couplings. It's certainly true that the boundary theory has new divergences, but that shouldn't scare us. That's something in some sense that is very familiar from the context of quantum field theory in curved backgrounds. So here I've written a counter-term action. This is my UV scale, and so this I might think of as the infinite contribution to the energy density or the cosmological constant. Even with constant couplings, there are going to be similar contributions. If this was a mass, this would be like lambda squared m squared, again, just to the cosmological constant. And here I might have mass to the 4th and some logarithm. Given that the couplings are time varying, I can write down other interesting terms that involve the derivatives of lambda, and they appear with the appropriate powers of the coupling as well, or the UV cutoff. And so this isn't scary at all. ADS CFT, just you follow your nose, it takes care of it all. Of course, there are these new divergences. In particular, there may be new log divergences which lead to new scheme dependences, and there's an interesting discussion in the papers, and I'll invite you to go read about it. But in today's talk, I'm not going to make you suffer through any logs, and so we'll just skip over that point. So that's lesson 1. Quantum field theory just works the way it usually should, and we shouldn't have any philosophical lunchtime discussions about whether or not this really makes sense or not. Lesson 2 is that when I'm doing a very fast quench, when I'm making that window smaller and smaller, there's an interesting universal scaling in various observables. And so here are 2 examples. If I look at the maximum of that response, what you find is that it's scaling as delta t to some interesting power that's governed by the conformal dimension. Similarly, the change in the energy density or the amount of work done also scales in that same way. And so that's a very elegant formula, which I hope will come back. And as a string theorist, I might have been satisfied at that point. I might also say that there are logarithms that kick in at special places for special values of delta. But again, we're not going to worry about those today. However, it's also rather annoying. Delta E is a physical quantity, and what we're saying here is that it diverges as the window or the width of my kick goes to 0. And so one might ask, is that really a physical issue, or is it simply a problem with my perturbative expansion? After all, I said I was doing an expansion in the amplitude of the field. Here I'm saying amplitudes are getting large. Surely I'm going out of the regime where I expect my perturbative results to give me a reasonable answer. I should also say, why am I wringing my hands? Why am I worrying about an instantaneous quench? Well, in the seminal work, the work that I originally read by Calabrese and Carty, the instantaneous quench is the basic starting point. They just say, I'm going to start with my quantum field. It'll have 1 mass, and then at t equals 0, the mass changes to a new value, and we watch how the system evolves. And yet here our holographic results are saying, well, there's actually a problem if I try and take this limit where the quench is instantaneous or where my jump is abrupt like that. So, no, I don't think so. But I'm going to spend the rest of the talk basically trying to resolve this issue. But before moving forward, I wanted to say there is one hint from, again, Paul and Larry. They were doing a full nonlinear analysis, and they remarked that in their case, with a marginal operator, that delta E went like negative delta t to the -4. In that case, it's just dimensional analysis. There's no other scale in the problem, and so it had to go like that. And so this really does seem to be, in that particular case, unrefutable that it really is a divergence there.
Sorry, why is this not due to uncertainty principle?
Because of the next 19 slides. So ask me again in 19 slides. I'm not sure. It may be jet lag as well, but we'll keep going. So let's just think about what we're going to do. I want to try and resolve that question. I want to think about this limit a little bit more, but I'm going to change my strategy. The first thing I'm going to do is I'm going to think about quenches that really take place in a finite amount of time. So the coupling is doing nothing up to t equals 0. It makes a transition through some protocol to a final value, and then it does nothing after t equals delta t. Then I'm going to ask the question, a very specific question, how much energy got pumped into the system? That was something that was giving us a problem. But to ask that question, I really only have to now focus my attention on this time interval. This is the only time interval over which lambda is changing, and so it's the only part of the protocol where I'm actually doing work on the system. And so that's where I can find the answer to this question. In the bulk, the influence in that short time interval is also going to only reach into the ADS space some small distance. that's basically proportional to delta t. And so this is certainly a more economical strategy in that I don't have to worry about that part of the simulation up there. I can I can focus my attention on that little triangle there. Now the limit I wanted to take was to keep that amplitude the same but squash delta t. So I want to go down like that. And I see in the bulk I'm now looking at a smaller triangle. I squash it again, I look at an even smaller triangle. And so the economy is getting even better and better. I'm certainly going to not have to work as hard in my numerical simulations, but it might also be a regime where I can solve using purely analytic techniques. I should say this is happening because I'm asking a very specific question. Delta E will let me fix the properties of the final state, but it won't tell me about all of the details, the exciting evolution that gets me from the end of the quench to that final state. And so I'm still going to have to rely on Luis and his numerical simulations to answer those questions. But in any event, let's focus our attention on that question. Here are some equations. You might recognize a scalar field. You might recognize a mass. You might even recognize a rho. But I haven't told you what the metric is, and so the rest of it is all garbage. It's just there to intimidate you to say that there are some really hard equations that one has to tackle to answer this problem. But rather than launching forth and solving, let's think about what would the solution look like. Remember that we're studying just a little triangle near the boundary. And so here's phi. The scalar field is going to look something like this. So there are parts here that you might recognize. This is the coefficient of the first independent solution. That's the one that we associated with the coupling. Here's the parameter that was associated with the second independent solution, and that's our expectation value. But as well as those coefficients, there are derivatives of those coefficients here and here. The equations are nonlinear, and so there's also powers. If there was a phi cubed term in the potential, I'd get a contribution looking like that. Einstein gravity is going to force me to introduce that term. And there are also combinations of the two appearing together in various ways. So all in all, it looks like a big mess, but actually it's not. ADS CFT organizes this, or the ADS space organizes this in a very nice way. And it's essentially in a way that says, this field is dimensionless, and so if I scale everything by their engineering dimension, then, well, this doesn't change at all. And so I have to, if I scale P naught by its dimension, which is d minus delta, then, well, that's soaked up by the scaling of the radius here. But I also know that when I have derivatives with respect to t here, that those are accompanied by powers of rho, again, to cancel the scaling. And similarly, you know, all of these terms are all organized in a way that the derivatives and the rhos all appear with very specific powers in order to make sure that this is dimensionless. Now that's a gift from ADS. It's not the scaling that I'm really interested in, but it does tell me that this is organized in a very specific way. What's the scaling that I want to do? Well, I wanted to think about squashing the time direction, or this delta t, and so what I'm going to do is I'm going to pick some fiducial time that I'm just going to fix in the problem, and then I'm going to introduce a parameter alpha, which I'm going to vary. In particular, I'm going to make it smaller and smaller, and that will shrink my delta t right there. At the same time, although I'm keeping the amplitude of my coupling, which was this coefficient, fixed. In doing so, it's very natural to scale the coordinates. If delta t is becoming smaller and smaller, then the interval that I'm looking at is becoming smaller and smaller, but it makes more sense then to work with a scaled t hat so that the interval in t hat terms is always something of order 1, or of order delta t hat. And similarly, the distance into the bulk, I'll scale in the same way, so that the action here is, again, covers a range of order 1. But again, the amplitude I'm going to keep fixed. So let's try that scaling. In fact, it's also very natural to think that P2, the response, this is the thing I'm solving for, is also going to scale in some way. And so I just introduced some power of alpha, and I'm not going to fix it for now. But let's look at some of the exponents. So because of that organization, all of those terms appear with the same power. If we're thinking about a relevant operator, then this exponent is positive. That means this is a small number, but it means this is a small number squared, and this is a small number cubed. And so to leading order in this limit, I only have to concern myself with that first line. And I can forget about the next 2 lines. Now, I haven't told you what delta is, but even before I tell you that, I can tell you that this number is smaller than that number, again, because I'm thinking of a relevant operator. And so we can throw away those remaining lines as well. That means there are 2 pieces left. There are a lot of coefficients here that I haven't solved for, but I've reduced the problem to solving, well, taking this and this. Now, I'm going to be solving some problem in the bulk. So if I want to impose, say, some boundary condition, this was fixed by my initial choices. To satisfy the boundary condition, this term had better be scaling in the same way. Say if I want to say that the derivative of phi is 0 at some radius or something. That's not the choice we're going to make, but then I would want these 2 lines to scale in the same way. And so that naturally tells us that this delta should be this power here, minus 2 delta minus d. And if I make that choice, then everything in phi is scaling homogeneously, and I extract an overall power out like that. That's only part of the problem. In fact, I said that I was solving the full bulk equations, and so there are a lot of equations about geometry, about the metric as well. I'm not going to carry you through that, but I'll say that the conclusion is you can make similar arguments, and basically what it says is the geometry that we want to study, or the geometry that carries the information that we need in this limit, is just ADS space. That makes sense. I said that I was pushing us into a little triangle closer and closer to the boundary, and so the relevant geometry is just ADS space. And so what does that tell us? Well, it tells us I wanted to find delta E solving the full bulk equations, but I imposed a certain limit of these while approaching an abrupt quench. And what that told me is that, in fact, I only had to solve the problem that I had solved before, namely the linearized scalar wave equation in ADS space near the boundary. One footnote here is that this argument really only works for relevant operators, not for marginal operators. I really wanted that exponent to be a positive number in order to make this work. If that vanishes, then clearly the arguments that where I was throwing away terms aren't going to apply. So we're really thinking about relevant operators here. In fact, given that simplicity, or that simple scaling, we're basically home free with respect to the question that I asked before. Remember, P2 was scaling in a very specific way. That's what I associate with, or that's what's telling me what the response is. And so if I translate things, what that's telling me is that the response is scaling with this particular power of delta t. Similarly, I said that I was going to fix the work done by doing this integral. That's just an integral over my P2 and the derivative of P naught. And again, because of the scaling of P2, we get the same scaling in delta E. But this is really the solution for the full problem. Of course, it matches for d equals 4 to our previous results. But here, I can affirm that I'm going to get exactly the same answer if I solve the full nonlinear problem. And so given the choice here, we know what the answer is, although I decided last night that calling it a problem is an attitude issue that I have, and so I changed it and I said it's a physical effect. But it's not, it was not an issue with our perturbative expansion. In fact, by serendipity, we happen to be studying the right problem to answer this question already.
So,
Yeah.
does the first equation just follow from dimensional analysis?
In fact, I erased that, but both of those equations, as long as I know that it's a linear response, then the rest of that is dimensional analysis. If I know that's quadratic, then this again is dimensional analysis, yes.
So Rob, there's a problem called we tune a system across a quantum critical point studied by Holography and Kibble-Zurich.
Yes.
And they have some scaling, and this seems very reminiscent of that. I mean, tuning across a quantum critical point is similar to just turning on the most relevant operator, which has exponent 1 over nu. Would you get the same, is it connected?
I have nothing to say about that, but I'd be happy to discuss it afterwards. Okay.
So the non-trivial statement here, you say is that the first equation is proportional linearly in data lambda, not to some.
Well, that's one interpretation, yeah.
You say even if you work to all orders in data lambda, it will only, in the end, will be
Patience, it
linear.
gets even better. I can assure you. If you let me go forward, we're going to have even better answers later. Sorry, is there a question over here?
I had a question. So you haven't mentioned the work of Bhattacharya and Minwala, which
Yes.
is like a very similar kind of perturbative analysis,
Right.
coming to a. I don't know if they wrote these equations down, but they certainly concluded that you have to take, delta lambda to 0 as you take delta t to 0 in order to keep delta e fixed. That's explicitly in their work. Would it?
Right. Wait. Too transparent. And then there'll be an equation that I'll ignore, but you can read it. I did want to say that so far I haven't solved anything. I just did basically, as Hong was saying, dimensional analysis. But there is more in that paper. In fact, we've got a lot of analytic control over the behavior of the systems in these fast quenches. And so here I'm giving you an example. So this is something that may look kind of intimidating. There's an amplitude delta lambda. There's a time delta t. But basically that's a function that's just tuned to start here at 0, go up to 1 in the delta lambda units, and then come back down to 0 again. So that's an example that I happen to have graphs for of the kind of thing that you can do. And you can ask, well, what is the response? In fact, there's an analytic answer. Here it is. So here's that annoying factor of 16. This is the scaling that we talked about. You pick up a power of delta t, or t over delta t. And then these are the various terms appearing in that protocol. And they all appear with coefficients that we can solve for with gamma functions and whatnot. That's not very informative, so let's draw some pictures. This is what the response looks like when we focus on d equals 4, and then there's a series of deltas. And so the biggest delta here gives me the biggest response, and then they get smaller and smaller and smaller. But so that's just an invitation to go read the paper. There's much more than a scaling argument in that short paper. However, so we now solve the full problem, and we're getting this annoying behavior, or a divergence, as delta t goes to 0. And so usually in my talks, in particular in Texas, where Matt was last spring, I start wringing my hands about, well, what does that really mean about these abrupt quenches, and can we make sense of it? And I remind you that the reason I'm wringing my hands is because, again, the foundational work that I learned about quantum quenches from just uses an abrupt quench as their starting point. And so I would have a transparency like that, and I invite you to read it either now or later. But after presenting that at a workshop this spring, Sumit Das came up to me and talked to me for a while, and we just decided afterwards, well, the way to figure out what's going on is just use our protocol in the same framework that Calabrese and Cardy were working. And so what is that? That's a quench of the mass of a free scalar field. So the coupling then is the m squared for the scalar. The operator is just phi squared. And the dimension of that operator in an arbitrary space-time dimension is d minus 2. What we want to do is we want to quench that with a finite, a protocol that has a finite width, and then examine the limit that delta t goes to 0. So the first thing we have to do is solve the Klein-Gordon equation with a mass that looks like this. This is, again, the profile that I used in my, in the original numerical work. It's just a tangent that turns on around t equals 0 with a window delta t.
Is that a boundary scalar or bulk scalar?
This is not holography. We've stopped doing holography. This is just a free scalar field in d dimensions with a time-varying mass. So this doesn't look nearly as intimidating as the equations that I had up before for the bulk. And in fact, it's a worked example in Burrell and Davies. And so this has a, there's a full solution. We can just solve for the modes of this equation, of our new scalar. And they look something like that. And so that's very nice. Given that, what we can do, one of the exercises one can do is you can look at the two-point correlator for a given mode between different times. The reason we're doing that is that was an exercise, or that was a calculation in the work, this work that we're trying to make contact with. And interestingly, if we use these modes and we take that limit, delta t goes to 0, we recover exactly the same expressions that these gentlemen found in their work, where they just started with delta t equals 0. And so that seems to say, from that perspective, that there's no problem. This kind of behavior just latches on smoothly to the initial work that we were worried about. But the kind of question that we were interested in, or that the holography led us to ask, were things like, what's the response? So in this case, the operator is phi squared. What's the expectation value for this particular quench? Well, you just stick the modes in, sum over all the modes, and what do you find? Well, you find a divergent mass, of course, and so I stick in a UV regulator. But this is where our experience comes to bear. We know that this, the quantum field theory still works, and we shouldn't really worry about it. Of course, we expected UV divergences. If I had a constant mass, I'd be doing an integral like that, which if I expand for small m, gives me an expansion like that, and I see that there are divergences at various powers and of the maximum momentum and powers of m. And so I know that, well, how would I deal with this? I would just introduce a counter term in the effective action that would eliminate that term and any other problematic terms. And so we'll do the same here. We're going to add to that, or one way to deal with it is to subtract these contributions out of this expression up here. And I'm just going to write it for d equals 5 here, because then these two divergences are the only two divergences I have to worry about. This just was something proportional to k max. This one was proportional to the mass, but here we know the mass is time dependent. In fact, I'm going to use here that profile that we had in our Klein-Gordon equation before. So this is now a regulated expression. The counter terms are going to give us this, and this is then not responsive, or it doesn't care about the UV cutoff, and so I can let my integral run from 0 to infinity. So the counter terms give us then this regulated expression. Let's just see what it gives us. So I guess we'll just squeeze this in. So this is d equals 5. Here's my expression. What have I plotted here? Well, it's not quite the expectation value, but it's the expectation minus the adiabatic response. So if I took this through the protocol infinitely slowly, I go from different to different equilibrium configurations. And I'm just subtracting that out, and I'm saying this is the interesting dynamics that the quench is giving us. I'm showing you curves for different values of delta t. As delta t gets smaller and smaller, of course, everything's happening faster and faster. And so on this scale, I'm plotting delta t over time over delta t, so that everything happens in the same window. And you can see they all take off in the same way, and they all come down at about the same place. However, there's this progression, this nice regular progression as delta t gets smaller and smaller as I step to as I go from 1 to 10 in that series. So let's put it on a log-log plot and see if we can make sense of it. Well, look, that looks like a line, and at best fit gives us a slope of 0.9969, which kind of looks like the integer 1. So just for fun, let's compare. What would we have gotten with our holographic scaling where we had this result here? Well, the slope would have been that exponent there. The delta was d minus 2, so we should have expected to get a d minus 4. I said I was working in d equals 5, so I should have gotten a 1. Look, wow, that's a coincidence. But it emboldens us to say, well, let's try some other dimensions. Let's see what happens. It's harder to change the operator. We've got a fixed operator, but I can change the space-time dimension. And as I go from 7 down to 4, I should have expected slopes of 3, 2, 1, 0. Look here, 3, 2, 1. And this is one of those log things that I promised you I wasn't going to tell you about. I didn't really expect to get 0. I expected to get a log divergence here. And these data points, well, are all the blobs, but we're running a log fit through them. And so that seems to work out very nicely. So that's rather remarkable. The holographic scaling seems to be reproduced in this free field calculation. Again, this has nothing to do with holography. This is just a free field. But it raises a natural question, which is, why is the holographic scaling being reproduced by a free field? Because I've already run over time, I'm going to ignore questions from the audience, and I'll just suggest half an argument. So let's consider a theory that's a conformal field theory with a coupling. There's some protocol here that's got an amplitude delta lambda, and this is some dimensionless function that goes from 0 to 1 in a time. Well, if this is x, it would go from x equals 0 to 1. Let's apply conformal perturbation theory. That means that I write my expectation value. I've just arbitrarily chosen to look at delta, or the expectation value at 0. I put that exponential out here and think that I'm calculating in the CFT. Then I expand that exponential, and I, get lots of terms. One of the interesting things that this tells me is that that first term, the expectation value of a relevant operator in the CFT vacuum should be 0. I've also pulled out, for each one of these integrals or interactions I pull down, I get to delta lambda that I pull out in front of the correlator. Then the only scale in these correlators is delta t. And so again, on dimensional grounds, I expect to get an expression that looks like this. So this has an interesting form. In fact, this is what we were seeing, but there are lots of corrections to that. But, just to skip ahead, what we should really do is think that that's organized in terms of a dimensionless effective coupling given by that product of the dimensionful coupling delta lambda, or amplitude delta lambda, and this window to the appropriate power. And so the first term is power g because the 0th order term vanished, then there's g squared, et cetera, et cetera, et cetera. But in fact, I'm looking at a limit where delta lambda is fixed while delta t goes to 0. I'm assuming a relevant operator, so that's a positive exponent. That means that this coupling is also headed to 0. And that means we're in a regime where that's a really good expansion to be making. And of course, it's going to be dominated by that leading term, which is precisely then the scaling that holography taught us, but then we saw in the free field theory. And that half an argument says that in fact that kind of scaling should be appearing quite generally. I've run over, and so here are some slogans, the 2 things you have to remember, and then the advanced lessons. So thank you for your attention. Larry. Oh. Larry. Oh.
I wanted to make a quick comment.
Okay.
Your linear response result, where you wrote the change in energy as a time integral of lambda naught prime to lambda 2 or something, right? You can reclass that as a completely standard linear response result, of course, because you're just doing linear response.
Yeah.
Right? And you get a frequency integral of frequency times the imaginary part of the spectral density of the response function that your choice of operator couples to.
You're going to explain this later, right? No, I'm just okay.
You know,
Keep going. Finish.
So, whether you get an infinite shift in energy or not, it's all about the high frequency behavior of that linear response function. And whether you get the same result as a free theory, then has to just be whether the high frequency asymptotics of this particular response function is the same in your holographic model and in your
it's right. It's about the UV fixed point. And something I didn't add is that most of CC's work here, this exponent is negative, and so they didn't expect to get a divergence. But there's more of a story to tell there, which I don't completely understand, but we'll just leave it. So you're going to explain that comment to me tomorrow. And Conrad has a question.
I was just wondering, I mean, as you mentioned in one of the earlier slides, you have to do the holographic renormalization very carefully, but that secretly means you add another scale in the problem, your UV cutoff scale.
Yeah.
And generically, all these naively like limits where delta t goes to 0, you can take them, but strictly speaking, all those distributions have a finite resolution at the
no, absolutely. If I have a system with a real cutoff, like if I'm working with an atomic system or a lattice or whatever, there's a real cutoff, and eventually I'm going to run into that cutoff, and that doesn't. Here I've explained just the systems, the field theories that I'm talking about. I've just assumed there's degrees of freedom all the way to infinity. And that may not describe a laboratory situation. I think that's what you're saying.
Well, I even mean in this theory that, strictly speaking, the limit of delta t to 0 goes singular, but there is a UV cutoff in the system.
Yeah, so then it becomes an order of limit.
It really becomes 1 over or order of the UV cutoff.
Yeah, sure.
If not, then nothing more.